Hello, and welcome to the last module of this Cantera course. Today, we will start the module on flames and see how Cantera solves flame equations. There are various types of flames that you can simulate in Cantera. It can be a free flame, a premix flame, a counterflow diffusion flame, and things like that. The only difference from previous modules is that now we are stepping into a one-dimensional domain. Up until now, we were solving equations in a 0D platform. So whether it was equilibrium or kinetics or things like that, they were mostly done on a zero-dimensional plane. Now we are getting into one-dimensional equations. So the way, like I said, the way Cantera handles flame simulations is in a 1D format. What that means is that Cantera, when you start a flame simulation in Cantera, the first step is to generate a grid, a one-dimensional grid, as you can see on the screen. And there will be two endpoints, which will define the domain of the grid. And then this entire grid will be further discretized into several other points. Now, the physical bounds of this grid initially are specified by the user. So you can give how long the grid should be. And as soon as you specify internally in the memory, Cantera automatically discretizes the whole grid into several points. You don't really have to mention about that. And as the simulation progresses, so each of these grid points, at each of these grid points, the flow equations are solved. And as the simulation progresses through time, Cantera keeps looking at gradients of various flow parameters. So whether it is velocity, for example, wherever Cantera will see that, well, there's a steep change in velocity, Cantera will automatically add several points in that region so that the entire gradient can be well covered and well discretized. So that, again, that happens internally. And so there's very little that you honestly have to do when it comes to flame simulations on your own. Most of the stuff happens in the inside of the simulation. So, and the last part is that since we are stepping from a 0D to a 1D domain, now transport properties are also very important. So the input data file that you use for a flame simulation should also contain the transport properties, which would be the viscosity, thermal conductivity, and so on. So with that, let's jump to Spider and see how these things are done in practice. And again, for this particular exercise, we will not really write a code or a script. We will work mostly on the console just to see, because this is a very this is the first class on this topic. So just to understand how each command behaves, we will work on the console. So let me bring up Spider. Okay. All right. So, well, the beginning, as you already know, I mean, it's the same drill. You have to import Cantera and then define an object and so on, and then also prescribe the phase. So let's start with the same thing. So we will say import Cantera as CT. And then again, it'll be just gas equals CT dot solution. We will again use GRI just to keep things simple, YAML. Okay, and next we will define a mixture. Let's keep it at stoichiometric, or maybe a slightly lean would be okay as well. Let's see. So gas dot TP, or let's just say TP for now. This will be temperature. Let's keep it at 300 and pressure at 1 atmosphere. Right. Now, gas dot set equivalence ratio. Let's set it to 1. And this time let us use ethane, for example. So C2H6. C2H6. And then the oxidizer will be oxygen 0.21 and nitrogen 0.79. Right. Okay, so now the gas has been, the phase has been set exactly how we've been doing it so far. Now comes the difference. So for the next line, we will start to define a flame object, object of the flame class. Let's go quickly check the documentation of the flame class as well. So I will bring up a browser. All right. And so this is the Cantera official website. We go into documentation. And here you see one-dimensional reacting flows, free flames, etc. And so just click there. These are all the different kinds of flames you can simulate: free flame, burner flame, counterflow diffusion flame, counterflow premix flame, impinging flame, ion burner flame, etc. And then you can go into each of these and read about them. It describes exactly what it is. We will start with the free flame. So if you go to free flame, this is how you define, that's the class, free flame. And this is how you specify the gas mixture, and you also give a grid and a width. Width is the total domain size of the one-dimensional grid. And the grid itself is, you can define the points, the intermediate points of the grid between the start and end and domain. But that's optional. So the best practice is to not provide the grid and let Cantera define its own grid, because it knows how to do it much better than we can tell. And so all we will do is specify the gas, the phase, and then specify the domain size, right? And rest everything will happen in the background. So let's do that. And you can read through all of this. The grid, width, all the definitions have been given. If you scroll down, each of the different flame type has its own description, and it's the same thing. You have all of the functions specified as well that you can access. So let's go here and go back to Spider. Right. So let's define width as some size. So let's say width equals say 30 millimeters. So it'll be in meters is 0.03, right? And then we specify the flame object. So it will be free flame, and then the phase, which is gas, comma, width, which contains a number 0.03. Width equals width. Right? We say enter. So I forgot to use the CT.free flame. Okay. All right. So now we have the object defined, which is called F. That's a flame object. It has the entire width of the grid. Now let's look at the grid itself. What has Cantera done in the background? So we will write F.grid. And here you have it. So you have the domain 0 to 30 millimeters. And all of these intermediate points is what Cantera has kind of input on its own. All right. Now, let's also see what it has done with initializing the grid. So we will, let's plot it, for example. So import matplotlib dot pyplot as ELT. Right. Now let's plot, let's say the velocity, for example. So, or the temperature. let's start with temperature. So plt dot plot f dot grid, comma, f dot t. All right, so here we have it again. So on the y-axis, you have the grid. On the x-axis, you have the temperature. So all the points in the grid have been initialized to a temperature of 300 Kelvin. Okay. Now, similarly, let's look at, say, velocity. So instead of temperature, we will write velocity. And again, you have it's all 0 and on all the grid points. Okay. Now, how about the mole fraction? So plot f dot grid. Then here we'll have to write exactly like we've done in the past. So x gas dot species index. Let's look at C2H6. Can't see. Okay. Okay. All right. So this is it. So here, x-axis, you have the grid. On the y-axis, you have let's see. Okay. So C2H6. The initial mole fraction was 0.056604, which is what Cantera has done as well. So what has been done here, and again, this is the same thing for, let's say, density. So we can look at density as well, f dot density. Okay. So that's 1 point somewhere slightly below 1.18. And you can just look at the values as well. So let's write f dot density. Sorry, the spelling is wrong. Density. Okay. So the exact density at each data point is 1.174. Right, and this density comes from ideal gas law. So you have the temperature, you have the composition, etc., and so you can calculate the density. So that was it for this class. So we've seen how we define the flame object and what happens when we first define the flame object. How is a grid created and what kind of initialization happens on the grid. For the next class, we will look at how to solve this grid. Right, so I'll see you in the next class. And thank you.